shall we? Let's do it. Yes. Astrophysics. Yes. Stellar atmospheres. Yes. It's like a football team or something. Yeah. Let's tackle some astrophysics. Yeah, you got black on our eyes. Yeah. Don't have too much reflection from the board. Exactly. Yes. Okay.
Protect the eyes.
Yes, it's very
From
important.
the photons.
You know it. That's right. Yes.
Those high energy guys.
Yeah. Yeah. Okay. So we were talking about optical depth, and so right. So we had this business where I naught, I lambda was I lambda naught, e to the minus tau lambda. And I'll redraw our picture where we pretend that there actually is a nice well-defined top of the atmosphere, which could be Earth's atmosphere, could be a star's atmosphere. Of course, we're usually thinking of a star's atmosphere. And so we've got some point of, in there we're calling the source. Yep. And straight up to the surface is the z direction. Right, but we're looking along some other line of sight. S is increasing that way. Lambda 0 there. So lambda increases the other direction. And we found that lambda is I lambda naught e to the minus tau lambda. So put another way, the optical depth at any given wavelength is the natural logarithm of the specific intensity that the light started out with at the source divided by how much specific intensity actually makes it to us. And that's what the optical depth is. So the optical depth is 1 when 1 over e is the fraction that made it to us, or put another way around. The original intensity was e times bigger than the intensity we actually received, would be that the optical depth is 1.
And then e squared.
E squared times bigger, the optical depth is 2. E cubed times bigger, the optical depth is 3. E to the 9.744224 times bigger, the optical depth is 9.72244. Maybe I actually said that correctly, I don't know. But anyway, that's the idea. Now, we call the geometrical depth the vertical distance down to the source. Yeah, so geometrical depth increases vertically downwards from the bottom of the atmosphere. So the correspondence between optical depth and geometrical depth depends on this angle theta that we are looking at the surface along. Because clearly, if we're at a slant like this, then the depth along the line of sight is going up faster than the geometrical depth is. Okay, so we have to account for that. Optical depth corresponding to a given geometrical depth. Depends on the value of theta. I'll just say depends on theta. And we often talk about a plane parallel atmosphere. And what we mean by it is, of course, the star is really spherical. And so really the surface of the star is curved. But on the other hand, if we were relatively close to the surface, then it looks awfully flat. And we make the same kind of thing with Earth. Earth's atmosphere, of course, is curved. It's got a radius curvature equal to the Earth's radius. But on the other hand, the ground looks pretty flat wherever you are.
Yeah.
And so when we talk about air mass in observational astronomy, as a first approximation, we can assume that we're standing on the ground and the top of the atmosphere is this straight line above us. In reality, it's an arc above us because the atmosphere is curved. But to a first approximation, we can pretend that it's flat. And we do that near the surface of a star. So if you want to get fancy, when you're studying a stellar atmosphere, you account for the curvature, for the fact that it's part of the sphere. But you can often get away with the approximation that it's plane parallel, that the layers are just slabs, if you will, as opposed to bent things, curvy things.
Even in the geography diagrams when they talk about atmosphere, it's like a straight cube.
Yeah.
Cuboid.
Oh, yeah. Yeah, right. So we're doing the same kind of thing. We're just assuming that it's in nice flat layers. So in other words, we're pretending that the flat earthers are right. Shut up, flat earthers. Don't think that I'm affirming you by saying this. For a plane parallel atmosphere, tau lambda, integral from 0 to s of kappa lambda rho ds prime, because we're good mathematical citizens. If you want to put that in terms of z, we would write that we're integrating from 0 to h. So h is the geometrical depth of the source, how far below the top of the atmosphere it is in the vertical direction, of kappa lambda rho dz over cosine theta. Because note here that for any little triangle I make, right? Yeah, any little triangle I make, dz is there, ds is there, there's theta, so dz is ds over the cosine of theta. But we've got another name for 1 over the cosine of theta, secant theta. Yeah, so we can say that this is secant theta times integral from 0 to h of kappa lambda rho dz. Excuse me. Well, this is what we call the vertical optical depth. In other words, if we were looking straight down at theta equals 0, then that would be telling us the optical depth along the line of sight where theta is 0, the vertical optical depth. So we call this, excuse me, tau lambda v, tau lambda comma v, the vertical optical depth. So we can write for a plane parallel atmosphere that the optical depth along any line of sight is the vertical optical depth times the secant of theta. This is where in limb darkening, it's related to that idea, because we can, so to speak, there's no sharp limit to how far we can see, but we can only see so far along this line of sight, if you will. And so if we can only see to a certain optical depth, and we can't really, but in other words, the vertical optical depth, sorry, the actual physical depth below the atmosphere corresponding to a given optical depth along the line of sight varies with the line of sight. So this is a fancy way of saying if I look straight down, suppose I said I can see down to an optical depth of 1. That's not right. You do get photons from deeper down than that, but suppose you were kind of calling that the cutoff. How far could I see if I could only see to an optical depth of 1? Well, that would be a certain distance if you're looking straight down, but a smaller vertical distance if you're looking at an angle because of the fact that you're looking at an angle. So if I could see this far looking vertically, then if I kind of rotate that around, I can only see down to here, closer to the surface if I'm looking at a slant.
It's like comparing depth and absolute depth.
Yeah, in some sense, right? Yeah, how far you can see along the line of sight is corresponding to a different how far you're seeing below the surface. And if the temperature is increasing with depth, then that will lead to limb darkening because you can see, as we keep saying before, deeper, hotter layers when you're looking straight down on the surface than when you're looking at a slant. This also ties back to something else we've talked about before. If you turn it around and the source is a star above the atmosphere, and we want to see how bright the star looks at our location, the idea is, here's us down on Earth's surface, there's you looking at the star, and how much obscuration you see depends on how long a path through the atmosphere it follows. And straight up is the zenith. Z is what we call the zenith angle, the angle of the star away from the zenith. And if we call x the air mass before, right, then if we define straight up to always be an air mass of 1, then the length along the line of sight here is a secant of z times bigger, right? So for the plane parallel atmosphere, this, at angle z, you're looking along the line of sight through the atmosphere, which is the secant of z times the vertical distance you're looking. And so if you define the air mass to be normalized to be 1 looking straight up, then the air mass in the plane parallel approximation is the secant of z. And so how much the starlight is dim depends on the secant of z, the secant of the zenith angle. It's exponential because the same effect applies. In other words, you get that how much we see is I lambda naught e to the minus tau lambda, and that'll have the optical depth will be some value vertically up, and if you look at angle z, the optical depth is increased by a factor of sec theta compared to if you're looking straight up. Yeah. So our stellar atmospheres and our Earth's atmosphere, similar considerations apply. So that's why stars get dimmer when they're closer to the horizon, and they do so in an exponential way with the secant of z, except when you get really close to the horizon, and then you start to have to account for the curvature of the atmosphere.
I see.
Because it's no longer true, right? If the atmosphere is curved, that changes the ratio. The path isn't quite secant z longer anymore. It's a little bit less than that.
Because it's the distance the star is moving in the sky.
Yeah, so in other words, if you take account for the fact that Earth's surface is really curved, then if I'm looking at the star at some zenith angle z, the path through the atmosphere isn't quite as long as I would predict if the top of the atmosphere is a straight line as opposed to a curved line. So in other words, the star will be a little brighter than I would predict for a plane parallel atmosphere. The curvature helps us a little bit because we're not looking at quite as much atmosphere. Yeah, it shortens the path a little bit. And, because if you think about it, in the plane parallel approximation, for a star at the horizon, you're looking through an infinitely long path through the atmosphere. But you're not really, because the atmosphere is only so thick, so you're never looking through an infinitely long path through the atmosphere. So, what else did I want to say? Oh, the other thing is that in general, the opacity depends on wavelength, and that's why there's reddening. Things get redder as they get close to the horizon, because tau lambda depends on wavelength, and it's larger at shorter wavelengths than it is at longer wavelengths, because there's more absorption and scattering at shorter wavelengths by the atmosphere than there is at longer wavelengths. And similarly, there's more limb darkening through the B filter because there's more scattering at short wavelengths in the stellar atmosphere than there is at long wavelengths. So the B filter has the most limb darkening, I filter has the least limb darkening for the BVRI filter set, for example. Because there's less scattering at longer wavelengths. Okay, what questions do you have?
Just one.
Yeah.
Tau lambda is dimensionless?
It is, yes. It's dimensionless because it's the logarithm of a ratio of specific intensities, and a logarithm has to be dimensionless because you can't take a ratio that has dimension. I mean, you can take a ratio, but logarithms are dimensionless.
So when we talk about optical depth, how do you picture it?
How do I picture it? I don't picture it per se. In other words, I don't try to picture it in terms of geometrical depth. It's given by this formula. And so I think in terms of how hazy something would look at various optical depths. The idea is, I like to think of a fog, okay? If this room were filled with fog, then if I'm close to you, the fog hardly matters. You can see me perfectly fine. You know, in a typical fog, even if it's pretty heavy fog, you have no trouble seeing your hand in front of your face. It'd be a really thick fog if you couldn't see your hand in front of your face. That's because your hand is at a very small optical depth away from your eye. And so therefore that ratio is very close to 1, and so the optical depth, the logarithm, is very close to 0. If the ratio were 1, the optical depth would be 0. At an optical depth of 1, only 1 over e of the photons are making it to your eye without getting scattered. And when you're seeing something, an image of something, what you're doing is that all the light rays coming from a given point on the object are focused to a corresponding point on the image. So only photons that make it all the way to you in a straight line from the object get accurately focused to a corresponding point on the image. So a fog, I'm still seeing light from every which way, but those photons are coming from some random direction after they scattered off a fog particle, not from the object that emitted them, or that I'm wanting to see that reflected them. And I see photons on my retina corresponding to the direction that they're coming before they hit my eye. And so to image something, you need the photons to come straight to your eye without taking any detours, so that they'll appear to come from where they actually came from on the object.
Not some reflected image from the particle.
Yeah, not coming from some random direction. So if I've got a flashlight in the fog, then, imagine the room's filled with fog. Turn off the lights. I don't see anything. Then I turn on the flashlight. So the whole fog will light up because of scattered light from the flashlight. But to see the bulb is only photons that come straight from the bulb, don't hit any fog particles, and then hit my eye and then focus onto an image of the filament of the bulb, for example. And if the optical depth is 1, then the filament looks dimmer than it did before because only 1 over e of the photons are making it to be. If it's 2, it's even dimmer, only 1 over e squared of them.
And then they cube and even.
And so on and so forth. Yep.
Okay. That's good.
Or you wanted to write something down?
Yeah.
Okay. Go for it. Yeah. I hope I can erase this stuff over here.
Yeah.
If not, too late, watch the video. Yeah, oh no! Okay, so now we're going to make a list of sources of opacity, of non-transparency in a stellar atmosphere. If the atmosphere was not opaque, we'd see all the way into the core, but it is opaque. So, number one, bound absorption. And this, the bound means an electron starts attached to an atom, it absorbs a photon, and when it's done, it's still attached to the atom. In other words, what we're talking about here is atoms absorbing photons and an electron jumps to a higher energy level. We're talking about making absorption lines, essentially, that kind of absorption. So bound absorption occurs when an electron bound to an atom absorbs a photon and jumps to a higher bound energy level. Occurs when an electron bound to an atom absorbs a photon and stays bound to the atom, but in a higher energy orbit. Now the opposite of that is the electron can drop back down again. So there's multiple possibilities. So one is, for example, have a hydrogen atom in n equals 2, photon comes along, kicks it up to n equals 3. Now that electron, well let's have it start in the ground state. So n equals 1, photon comes along, let's say kicks it up to n equals 3 for a hydrogen atom. Now, if it drops back straight down to n equals 1 again, you can think of that as the net effect is a scattering because the photon will be re-emitted, but in some random direction that's not likely to be the same direction as it originally came from. And so the net effect is, you can think of it as, yeah, the photon disappeared for a while, but it might as well have just done that, just changed its direction, because the emitted photon has essentially the same energy as the absorbed one because it's the same levels. You have to account for the kinetic energy of the atom, but that's a very slight shift. So it's practically just a scattering. On the other hand, that photon could disappear, it jumps to n equals 3, and then it goes to n equals 2, and then it goes to n equals 1. So then what happens is one photon has its energy split into a pair of photons. The original ultraviolet photon of some higher energy becomes now a red photon from the 3 to 2 transition plus a lower energy UV photon from the 2 to 1 transition.
I see.
And in the star, all that stuff is happening in the atmosphere.
Wow.
Yeah, so it's a mess. If the E minus drops back down to the original level, the net effect is a scattering. It's just redirected. In which, quote unquote, the photon's energy stays the same, but its direction changes. Really, it's not quite the same because because really when an atom absorbs a photon, you have to conserve momentum, and so the atom also recoils. It picks up a little kinetic energy. So the photon actually has to have a little bit more than the energy of the transition if it's absorbed by an atom at rest, because it has to give it some kinetic energy as well as cause the transition. So in which the photon's energy stays almost the same, but its direction changes. And I put the photon in quotes because, well, it disappeared for a moment, and now there's a new photon. So, yeah, it's kind of a philosophical question. Is it still the same photon? Or is it a new photon?
Yeah.
It doesn't matter, is what it comes down to. A photon, it's a photon, who cares? So on some level you just say, well, it's as though a photon just redirected. Yeah, it disappeared for 100 millionth of a second or whatever, but whatever. How many photons can dance on the head of a pin? It's like, so we're not going to worry about any philosophical questions about, is it really the same photon? If, on the other hand, the electron makes multiple downward transitions through intermediate energy levels, the effect is a degradation of the mean photon energy. You have same amount of energy in the end, but it's split among several photons. So the average energy per photon goes down. That's part of the process. That's part of the process that turns the gamma rays emitted by nuclear reactions in the sun's core into visible light and infrared light and ultraviolet light by the time it comes out of the sun's surface. Is each gamma ray photon's energy has been subdivided so that by the time you get to the surface, that gamma ray photon has become many, many photons of lower energies.
I see.
Right. Now, is it still the same? Shut. Go ahead. Yeah.
If there is no if there was no scattering like this or redirecting, would like the gamma rays coming out of the core, we would just straight up see the gamma rays?
Yeah, if the sun's atmosphere were not opaque, if it were completely transparent, we'd be being bathed in gamma rays coming from nuclear reactions in the sun's core.
We'd be completely.
We wouldn't like this.
Okay.
Yeah, we would hate that. Yes.
Wow.
Yeah, I don't recommend that.
Would we be still able to see the star though?
Well, the thing is you have to remember, so you have to remember that if you were inside the sun, sometimes people make this wrong statement that, oh, if you were in the sun's core, it's so hot that it's mostly gamma rays, and so it must be dark in there. Now remember that the Planck spectrum gets brighter at every wavelength as the temperature goes up.
Yeah.
So there's plenty of visible photons that would be coming out of the core as well. But we would also be getting doused with gamma rays.
Yeah. Okay.
Which, again, I don't recommend. You lose your day if you're doused with gamma rays.
It didn't work out well for Bruce Banner.
Yeah, that's right. That's good science right there. If the electron makes multiple downward transitions, through intermediate energy levels, the net effect is a degradation of the mean photon energy. radiation, an overall reduction of the mean photon energy. And I always want to say something stupid, but the nice photons are unaffected. It's only the mean photons. So how much would you pay? Don't answer yet, because wait, there's more. For no additional charge, we'll throw in bound-free absorption or photoionization as our second source of opacity. So another name for bound-free absorption that you'll hear used is photoionization. Ionization by photons. And that means you have enough energy to strip the electron off of the atom.
Oh, so
It starts in a bound state, but the photon comes along, gets absorbed, and the electron comes off the atom. So for example, in hydrogen in the ground state, we remember any photon with more than 13.6 eV can ionize it. And so that's an example of bound-free absorption. So the name comes from the electron starts bound, but afterwards it's free, it's no longer attached. Yes. Yeah, so it's like, yeah, so, oh, I'm stuck on this atom, I'm sick of this. Oh, photon comes along, and then the electrons, I'm free, I'm free, I'm free, I'm free. Oh, damn, I got captured again. But, you know, it's another story.
Ouch.
Yeah.
Poor guy.
Yeah. So this occurs when a photon has enough energy to ionize an atom.
So, in this case, because the electron that absorbs the photon is, I mean, it moves out of the atom.
Mm-hmm.
So in this case, it was a gamma ray again re-emitted.
What'll happen is, so first of all, it can be, if you're in a really hot stellar interior, these processes don't really take place because there aren't any electrons bound. But if you're in a stellar atmosphere where the temperature is low enough for atoms to exist, to have electrons orbiting the nucleus, then both of these processes take place, and the inverse of bound-free absorption would be like free bound emission. In other words, the second part where it gets recaptured. Typically it doesn't go right into the ground state. Typically it's captured into a higher energy orbital, and then it starts cascading down towards the ground state. And so this would be another degradation in the end, because a high energy photon came along to ionize it. Then when it gets recaptured, it emits a bunch of lower energy photons. So the net effect tends to be to degrade the photon energy, to redistribute it to other photon energies. So all of these have an inverse. The inverse of bound-down absorption is bound-down emission, where the electron drops down. So, and I'm mentioning that, you know, the second part of it is the inverse of it. So, and an important thing to remember is that, bound-down absorption takes place at essentially discrete wavelengths. Electrons bound in an atom that stay bound to it are only allowed to orbit, to absorb photon energies corresponding to a transition energy. But this is different. Any photon whose wavelength is short enough so that its energy is high enough to ionize it can do it. So in the ground state, a 13.6 eV photon is the minimum energy, but 13.7 eV works just fine, 13.9 eV works just fine. The difference is, if you have more than enough energy to strip the electron off, the excess shows up as the kinetic energy of the electron after the ionization.
Okay.
If you need to write something, I'm gonna wait for you to do so.
I'm just copying.
Yeah, go ahead. I mean, I don't wanna like keep writing and you're just trying to copy, you know, so. So, and this is just, I'm just quoting this, we're certainly not deriving this, this comes from doing the quantum mechanics. For a hydrogen atom, in energy level E sub n, so it has a certain value of the n principal quantum number, the bound-free absorption cross-section, so sigma BF, the bound-free absorption cross-section, turns out to be 1.31 times 10 to the minus 19th power times 1 over n to the 5th times lambda over 500 nanometers cubed. And then the units are square meters because remember, cross sections are effective areas of the atom. So on some level, this is the area, if you will, the effective area that the hydrogen atom presents to a photon with enough energy to ionize it.
Wow.
If it's in the nth orbital.
How is this going?
It's a complicated derivation from quantum mechanics and electromagnetic theory. So. Yeah, it's not a trivial calculation, is what it comes down to. So we're going to be happy to just say, thank you, experts, for telling us this formula that you got. And I will note that physically what the cross-section is the number of absorptions per atom per second divided by the number of incident photons per square centimeter, per square meter per second, I should say. So in other words, what you do is you imagine, okay, there's this atom, and you send a bunch of photons of a given wavelength at it as a beam, and the number of photons crossing 1 square meter every second on their way to the atom is the bottom there, the number of incident photons per square meter per second.
I see.
And the cross